Okay, students, so we'll be discussing some useful operators in quantum mechanics. Remember, these are very, very useful operators in quantum mechanics, uh, which you'll be needing needing in your calculations later on. So first, we'll be dealing with the momentum operator. Though the way I have derived this operator is very basic, but still it will work. So the momentum operator along x, say the momentum along x, so px operator. In order to derive this momentum operator, I have considered the wave function psi to be this. So you need to believe me or trust me that the wave function of a particle can be written in this form. So it is AEI kx minus omega t, where you already know what k and omega are. So this represents the wave function of a particle. So if you though it's a wave function of a free particle, but still it will work in deriving the momentum operator. So we'll find out how we are getting this psi once we start solving our Schrodinger's equation, which will be coming in your next classes. But for the time being, you please trust me on this, that psi can be taken as kind of this. So differentiating this psi mathematically with respect to x, what we get? So d dx of psi, so if you d dx of psi, what you get is ik out. So you get an ik out, and this is nothing but psi. So you have ik psi. So I multiply both sides with minus ih cross on this side as well. So I square, this is the imaginary iota. So I is a minus 1 and there is a minus, so it becomes plus. So it becomes h cut k psi. So multiplying this on both sides, you get an h cut k psi. So what is h cut k? Now h cut k is h by 2 pi and k is 2 pi by lambda. So we get h by lambda, which is nothing but the momentum value. So h cut k is the value for momentum. So what do you have? Minus I h cut d dx of psi. You get p, that is the momentum value, h cut k psi. So isn't this the equation that I discussed in the previous class? You see the operator operating on psi, giving a value, and psi retaining itself. So you see this, I've circled it, this is the operator minus ih cross d dx, which if operates on psi gives you the value of momentum, which is the eigenvalue h cross k, and psi itself. So this, isn't this the momentum operator along x-axis, which gives you the momentum value? So this is the momentum operator. So thus the momentum operator px along x is minus ih cross d dx. Do not forget to put this minus sign. So it is minus ih cross d dx. Similarly, by analogy, I can say the momentum operator along y is minus ih cross d dy, and the momentum operator along the z axis is minus ih cross d dz. So I hope this is clear, that if I'm operating this on psi, I am getting the value of momentum, which is h cross k and psi. So this has to be the momentum operator along x. Similarly, this is the momentum operator along y, and this is the momentum operator along z. So next, very, very important is the kinetic energy operator. So what is the kinetic energy? Let's say I have taken the kinetic energy to be T hat, which is P hat square by 2m. Again, these are all operators. Kinetic energy is P square by 2m classically. So in terms of quantum mechanics, it becomes an operator which is P hat operator square by 2m. So 1 by 2m is a common. P hat operator square can be written as P hat x square plus P hat y square plus P hat z square. So you know Px or hat, this momentum operator along x is minus ih cross d dx. Similarly, Py operator is minus ih cross d dy, and Pz is minus ih cross d dz. If we square this, so this, if we square this, it becomes positive, but I square is a negative. So minus h cut square del x square. So you can see minus h cut square del x square del y square del z square, and 2m is a common. Minus h cut square is also a common. Why a minus? Because this becomes plus and I square is another minus. So a minus of h cut square common, 2m is a common, del x square del y square, and del z square. So this is the kinetic energy operator. So if I ask you the kinetic energy operator only along x, so this is the total kinetic energy operator, only along x, it would be minus h cut square by 2m del x square. Simple. Only this. These two parts won't be there. So this is the kinetic energy operator only along x. Now the total energy operator. This is also called the Hamiltonian operator. So again, taking psi as this is the amplitude and this will be the phase of this wave function. So you can see this is a complex quantity. So AEI kx minus omega t, another again. So differentiating with respect to time, this time t. What do we get? d psi of dt is minus I omega is out and this remains the same. So this is nothing but psi. So you have minus I omega psi. So again multiplying this time by I h cut. Again multiplying this by, this time this is not, the previous one it was minus I h cut. This time I am multiplying it by I h cross both sides. So you have I h cross into minus I omega psi. So this is what you have. So again a minus sign is there, but I and I is another minus 1. So it is minus plus. You have h cut omega psi. So I h cut d psi by dt is h cut omega psi. Now what is h cut omega? H cut omega is h by 2 pi. Omega is 2 pi nu. So you have h nu, which is nothing but the energy value. This is the value of energy. So h cut omega is the energy value. So I h cut d dt of psi is equal to the energy value, that is the eigenvalue and psi. Energy value and psi. So if you operate this on psi, you get the energy value and psi. So this is the total energy operator. So Hamiltonian operator, again it is denoted by h hat or e hat, you can say, is I h cross del t. I h cross del t. So if you operate this on psi, you will get the energy value, the total energy value, remember, and psi. So the Hamiltonian operator or the energy operator is I h cross del